Hello, my friends. We have another ideal gas problem here in physical chemistry, and let's just get to it. So an ideal gas thermometer of constant volume indicates a pressure of 5.69 kilopascals at the triple point temperature of water, which is 273.16 Kelvin. And the question is, what change of pressure indicates a change of 1 Kelvin at this temperature? Now, there's two ways to do it. There's the way that you probably learned in general chemistry is by treating this as a variable gas problem. And to do that, we write down the ideal gas equation or perfect gas equation, whatever you want to call it. And because the gas is changing, the variable values are changing, we indicate what's changing. And what's changing is the pressure and the temperature because we're holding the volume constant volume. And we put everything that's changing on the left and everything that's not changing on the right here. And we see that this right-hand side is comprised of all constants, so that's equal to a constant. So that means no matter how we change pressure and temperature, they have to equal the same constant. So we can say that the initial pressure over the initial temperature is equal to the final pressure divided by the final temperature. There. And we'll just plug in some values here. And now we're solving for the change of pressure, but we can get the change if we know the final temperature here, P2. So the initial pressure is 5.69 kilopascals, and that's with a temperature of 273.16 Kelvin. And we want the final pressure, and the final temperature is 1 Kelvin greater, so 274.16 Kelvin. So we'll solve for P2, just multiply these two, then divide by that one. So we'll have 5.69 times 274.16 divided by 273.16, and that's a lot of numbers. We don't need all those digits. They're not all significant. 5.711, we'll say. 5.711 kilopascals. We really only have three significant figures here. And so the change of pressure is equal to, of course, P2 minus P1, which is 5.711 kilopascals minus 5.69, whoops, not 96, not 69, almost did it again, kilopascals, and that's equal to, so I have this number from before, 5.711 minus 5.69 is 0.021, 0.021. 0.02, it says 208, doesn't really matter because there's only, we only have precision to the second decimal place here. So the change in pressure is 0.02 kilopascals. Alright, so that's using just first year material here. But there's really a more elegant way of doing this. And let's start off again with the ideal gas equation here, PV equals nRT. Now we care about the pressure, the change in pressure, so we'll solve for pressure with P equals nR over V times T. And we want the change in pressure over the change in temperature. So we want the change in pressure, the partial derivative of pressure with respect to temperature. This is the change in pressure over the change in temperature in a constant volume process. And the derivative of this right-hand side, that's what we do. We take the derivative of this left-hand side first, and now the derivative of this right-hand side with respect to t is just this constant here, nR over V. And we know what nR over V is. In terms of the ideal gas equation, nR over V is equal to P over T. It's equal to P over T here. And this P over T, well, we have a P and we have a T, so that's 5.69 kilopascals and over 273.16 Kelvin. And this represents the slope, the rate of change of pressure versus temperature. I'm just going to calculate this really quickly here. Move it down, and 5.69 divided by 273.16 is 0.0, we've seen this number before, 0.02083. So 0.02083 kilopascals. And this represents the slope. If we looked at this on a graph of pressure versus temperature here, this is a positive slope here. So it's going to go It's going to go like this, and this is the slope here. This is like your y equals mx plus b, similar, so this is your slope of it, the change of pressure over the change in temperature. And we want to know the change of pressure if the change in temperature is 1 Kelvin. So we can approximate this equation here. So we can say that this change in pressure over change in temperature at constant volume, that's the slope, 0.02083 kilopascals, 3 sig figs, approximately equal to dP at constant volume, 0.02083 kilopascals dt. Integrate both sides from P1 to P2, which will go from T1 to T2. This is the initial pressure, initial temperature, final temperature. And the integral of this is just our change in pressure that we want. And that's equal to 0.02083 kilopascals. And this is our change in temperature. That's our delta T, change in temperature, which is, I'll write it as change in temperature here, which is just 1 Kelvin here, 1 Kelvin. So change in pressure equals 0.02083 kilopascals times 1.00 Kelvin. And we don't have to subtract anything, so we're not going to lose as much precision as with the other method. 0.0208 kilopascals, delta P. All right, there we go. Hope you enjoyed it.